Good afternoon, everyone, and welcome to today's webinar on Eyesight. My name is Pratik, and I'm a technical manager at EDS Technologies, and I take care of all the simulation needs for our customers. And today, along with GS, we are going to deliver the webinar on Eyesight overview as well as optimization. So today's webinar basically is on Eyesight. That is, we would see how to automate design exploration and optimization, specifically with respect to the use of Eyesight. And the webinar will be delivered by Bharat. So Mr. Bharat is from Dassault Systems, and he is an industry process consultant for the brand Simulia at Dassault Systems. And Bharat comes with a vast experience in specifically in FE modeling, be it a full vehicle level, morphing as well as optimization. And he has worked with different customers like Tata Motors, M&M, HMC Korea, Toyota Europe, Honda Japan, for typically for projects as well as for supports. And currently through Dassault Systems, he is supporting all the different verticals with respect to the usage of optimization as well as design of experiments using Eyesight. And through the course of webinar, if you have any questions, please type it in the question box, and we will address to all your questions at the end of the webinar. So once again, thank you all for joining this webinar, and I would like to welcome Bharat on board and hand over this to Bharat. So Bharat, thank you very much for taking out your time for this webinar. And now you may start the webinar. Thank you.
Thanks, Pratik. Hope I'm audible. So good afternoon, everyone. Maybe as a part of this webinar, probably I'll first start with an overview on Eyesight. So maybe some of you are new to an Eyesight. So probably I'll quickly take you through what Eyesight is and how it can help you in your daily activities. And probably from there, we'll look into a few case studies as well. And at the end, I will also try to show a quick demo on how to use Eyesight and how easily can you actually create models in Eyesight. So that's how it might go. So let's get started. So as I said, maybe if you're kind of new to Eyesight, so what is Eyesight basically? So it's a you can call it's a platform where you can integrate multiple tools. So it could be a regularly used simulation tools, or it could be some other tools also, where if you want to do some level of automation, you can integrate multiple tools inside Eyesight platform. So it will workflow in Eyesight would look something like this, where code hand like structure, where you can integrate multiple softwares like I was telling. So there is an Excel here, as you see, and there's Abacus here, and there's something called data matching. So you can integrate multiple softwares at the same time. You can pass information from one next to the other. So as you see, probably information from Excel is going on to Abacus, and from Abacus the information is going on to data matching, something like that. Or you might have another, we call this as driver application, which kind of drives this whole process. So the driver component could be optimization, or it could be a DOE, or just a regular task which does the activity for one time, something like that. You can easily communicate between different softwares, and also in case if there are multiple files involved, wherein the parameter information, or sometimes the output of one particular activity, that particular file is required to run the next activity. So even that is possible. So not just the parameter information, but even files between different applications, and kind of automate. So in case if you are going to do a design exploration where multiple runs of iterate, so even that, as you see, runs in one shot. And at the same time, we have enough enough methods where you can view your results in a meaningful way to try to understand how your input is affecting your output, or how your actual relation between input output is, whether it's too non-linear or it's very highly non-linear, or whether it's linear. So all this visualization, you can see it in our results as well. So I was telling, we have, or we can use mainly Eyesight for two main concepts. That is one we call as SimFlow and others data flow. SimFlow is nothing but kind of integrating your own different tools. Like you see this big flow chart here, or there are multiple activities that are involved, and you can create a workflow as big as this or even bigger than this. So where if you have, let's say here, first Excel is there where some level of we are calculating some cost, and then there's a calculator which kind of converts the information. So you see X1 is input and Y1 is your output, and the same Y1, since it's just a conversion, there's no change in the actual value. So again, it's just Y1 is coming out, and this Y1 goes as an input here. Similarly, here we have X2 as input, and this is shared between both the MATLAB and the calculator component. So the same information is passing to both of these activities. And there's certain outputs that are coming out, and we kind of capture both the outputs here. So accordingly, if you want to create multiple loops within a workflow, as you see, there are two loops here. So you can create everything in Eyesight. So this we call as a SimFlow in Eyesight terms. It's a simulation workflow, what we call. So, and this is on our customer base. So all the major players in the market are our users, as you see. Then we will talk a little about the architecture of site. So there's something called as design drivers. So these are the which drive the uh, they have some level of kind of an intelligence to understand the output, and accordingly they'll vary the input. So be it DOE, different probably to give you an idea, you see that optimization is on top, and this is actually just driving all the entire. So this kind of gives you some level of input information process, and all the output information is segregated, and the output information goes back to the optimizations. If your objective, so probably your objective could be minimizing mass or something like that. So if the particular set of inputs are helping your outputs, so it kind of gives you a set of values which are closer to that. Or if it's not helping, maybe it will change the values and give a new set of values. Then we have application components, which are the regularly used softwares, be it Abacus, or if it's a MATLAB code, or you have KTA or ANSYS, FESafe, LSDyna, any of these. So these are all something which actually run, but they take the information from the driver component and they run, and accordingly the output response is again taken back into the driver component. So these are the ones which actually run the software. So creating a SimFlow in Eyesight, like I was telling, it's quite easy. So you just drag and drop any of the components here. So as I said, so there's something called process components. These are the ones which drive the whole process, and then in the other tab we have the application components which actually run the particular file. So we have two GUIs in Eyesight. So one we call as design gateway, and another we call as runtime gateway. Design gateway is basically, you can call as the pre-processing environment, and runtime gateway is the post-processing environment. So with design gateway, you can select the components and you can map the parameters. Like if you're going to have multiple activities involved, so you can map what parameter information should move from Abacus to the calculator, or if it's a bigger workflow, so accordingly from one activity to the other activity, how the information should pass. So that and all you can define in your design gateway, like you see here. So all the information between different activities, as you see, so this is how the information is passing. And you can create your own workflows, or you can define the graph templates. So you can define it earlier, or you can even create it in your runtime gateway as well. Like as you see, these are all your graph templates. And when it comes to runtime gateway, you can monitor the status of your run. Like if you're doing some 100 or 200 iterations, what is the state? So all that, so maybe it's at the 80th iteration, and whether it's passing or whether it's failing. So some of them might fail because of some design constraints. So accordingly, all that information you can view it in the runtime gateway. And you can view the parameter information as well. So how are the outputs values coming out, etc. Accordingly, you can even do the post processing where you can create some level of plots and graphs to understand your results as well. With respect to design exploration, like you can do multiple things in Eyesight. So one is definitely process automation. Like as I was showing you, you can kind of connect multiple tools, and you can create a automated workflow. That is one thing. And the other is doing a design exploration. Like if you want to update your design, if you want to create a more better design to meet all your constraints and objectives, that also you can do it in Eyesight. So out of those majorly used techniques are the DOE, design of experiment methods, and then we have optimization, and then we have quality engineering methods where you can kind of make your design more robust, you can say. And also there's something called approximations, so where you can create a meta model, etc. So in that first, it's design of where we have enough methods where you can create a good spread of your design space. So all these methods can help you. Similarly, with respect to optimization, so as you know, there are three main categories: the exploration, the direct methods, and the trade-off methods. So all these we have enabled in Eyesight. Then we have the quality engineering methods like the Monte Carlo simulation or the reliability-based design optimization or Six Sigma robust design. So all these methods are available in Eyesight. Similarly, with respect to approximation, so there are multiple ways of creating these meta models or mathematical models, or you can call black box models. They're all the same. So we call them as approximation models. So we have enough methods where you can create a good fit of your input and output response. So you can create the relation between your input and output. With respect to design of experiments, like I was telling, we have enough methods which you can use based on your requirement. So in general, the most used optimal latching hypercube we also have, and any other full factorial or orthogonal or composites, and the regularly used Latin hypercube or optimal hypercube, or if you have your own design matrix, that also you can load it into Eyesight. So this is just to give you an idea. So this is the I-beam section, and we are going to create a DOE. So it can change shapes accordingly. And these are some of the results that you can visualize where. So this kind of gives you, these are the correlation maps which can give you the relation between your input and output, like whether it is positively correlated or negatively correlated. So anything this negative sign says it's negatively correlated. Similarly, anything which is positive is positively correlated between. So this is all your you can call these are input parameters and these are your output parameters. So how is your relation in the relations? Parameters. Similarly, we have Pareto plots, which is the most that is affected. You understand that. So it's in red and reducing. Similarly, the other way, as you increase your other parameters like length and all, yeah, your stress is increasing. So accordingly, you can get a better understanding of how your input is influencing your output. So that idea you can get. And also understand how your whole your relation between any two parameters and your output, whether it's a linear or it's a highly nonlinear relation. Because as you see, this it's very wavy, and you understand that it's highly nonlinear. And also we have these data mining methods where you can kind of filter out some set of information like currently the beam height is in the range of 10 to 80. So maybe say 10 to 20, the values are falling. You can filter out what are all. So that way you can filter out some data and see the ones that are of your requirement. Then optimize it's just trying to find the best what we have. So and maybe start with the initial design and finally end up where your optimal is met. Accordingly, all your constraints and etc. are also. So just a quick kind of a overview how this has evolved. So all why do we do optimization? Basically to reduce your cost and your time as well. So in the regular conventional method usually used to be where you build the design, or sorry, you design it, then you build it, and then you test it. And after some time, so the analysis came into picture where you design first, then you analyze it, then you build it and finally test it. So this way you are kind of reducing both some level of cost and time. So with the evolution of optimization, what is happening? You optimize your design in initially itself in the analysis phase itself. Then you go with your detailed designing, and then you build it and validate it. So that way, if you kind of optimize it at the initial stages itself, before even creating the final design, so that way it can help you in both reducing the time as well as costs. So with respect to optimization methods, we have both parametric methods and non-parametric methods. So Eyesight is typically used for the parametric method optimization. Similarly, we have solutions for non-parametric as well, that is Tosca. So that we are not discussing now, but just to give you an idea, so the parametric methods way, yeah, we use Eyesight here. And then we have something called as MDO, multidisciplinary optimization, where you kind of involve multiple disciplines sometimes. So in this case, as you see, there's an airfoil blade that is there, and you have the CAD, then FE is involved, and structures and aerodynamics. So both, we have two disciplines involved, structures and aerodynamics. So usually when you're looking at a multidisciplinary optimization, how do you see it? So maybe what would usually happen is the first discipline might give you a best result somewhere here. So anything shaded in this color, you can imagine this is your first discipline value, and anything in this thick color, so this is the second discipline. So this will be your other value. Now there are, as you see there, this discipline, the first discipline gives you a minimum value somewhere here. The second discipline gives you a minimum value somewhere here. But what we usually look at is, so this region, right? So this is where both of them are kind of overlapping. So this is your feasible design space, we call. So when you're going with a multiple discipline, and the minimum of within this design space, as you see. So this is the value. So this we call it as the multidisciplinary optimal design. So maybe we can have individual uh, minimum values for each of the disciplines, but when you involve a multidisciplinary optimization, so the combination of both, where this region, the minimum of this is what we call as the optimal design. So with respect to optimization, so this is just some kind of terms that we use. So there's something called as design variables, where there's nothing but the input parameters that we add to kind of perform the optimization. So what are the values that you're going to change to see improvement in your result? So those we call as design variables. Similarly, there could be constraints. So constraints could be like equality constraint or inequality constraints. You can say your stress level should not cross so and so value, or your deflection should not cross or it should not be more than this particular value. So like that you can define your constraints. And according, there's always an objective. So objective could be this is where, this is what you're trying to do. So this it could be like minimizing the mass, or you can call maximizing the efficiency, so something like that. So that will be your objective. So this is just a small example to kind of give you an overview how it works. So imagine you have an I-beam structure like this, where it is fitted to one end and it's free on the other, and we are applying a load in this direction. So these are the two design variables that we are kind of varying in our optimization process, that is the beam height and the flange width, as you see in these structure. And then we have a constraint as well, that is stress here, wherein stress should not increase, or it should be within 16 megapascal. And then the objective is to minimize the overall mass. So how it works is, as you see, this region, so beam height, if you kind of plot this range 10 to 80, so this will be the region. Similarly, flange width, if you plot, so it's between 50 to 8, sorry, 10 to 50, and within this is the range. So this is because the design space. So this is the region which you're considering for looking out for the best result. And now within this, so there is always a constraint that is involved here. So that is stress constraint. Strength should be less than or equal to 16 megapascals, as you see. So now this, within this whole design space, now this region is what we call as the feasible design space. So this is your feasible design. So meeting this constraint can help you to search within this region. And so within this, we try to see how your mass is coming. So maybe we'll start with 400. It's coming like this. then the mass is around 300, and finally we end up with the minimum mass, which is also meeting your constraint as well. So it's like exactly touching your constraint curve as well. So this is your best design, you can say, and that is coming around 233. So this is how usually it works, the whole optimization process, when you have design variables, constraints, and objective involved. So general classification of optimization techniques, like there are main three categories, that is the gradient based techniques and the direct techniques, exploratory. So yeah, gradient based are, it can give you, if your model is simple, if you know, then you can go with gradient based. They are quite easy to kind of compute. They may not take much time. Similar direct are kind of intermediate level techniques, and we have exploratory techniques as well, which definitely, so maybe these two might, the initial two techniques might give you a local minimum in case your model is a very you can, if it's highly nonlinear, maybe you might end up with some local minimal, but exploratory will definitely give you a global minimal. At the same time, it might take more runs, or it might take more time to compute. And now we have something called as a pointer technique, which is kind of a automated technique we call, where the tool itself, if the user is new to optimization and he's not sure which technique to use, he can directly use this pointer method, so that the tool will take care. So it has inbuilt algorithms in it, like the linear simplex and NLPQL downhill simplex and evolutionary method. So each of one of these techniques are added to the pointer method technique. That way, the tool will try to understand, maybe within the first initial designs, it will try to understand how the model is. If it's highly nonlinear, probably it will go with the evolutionary algorithm, or if it thinks that the model is not so nonlinear, it's quite simple and linear, it might use any of the simple techniques. So the tool will take care. So we need not actually pick any particular technique. The tool can take care of it. And then we have multi-objective optimization also. So this is quite common these days. Now what is happening, so you might have more than one objective, wherein if you see this case, yeah, now we want to both minimize the mass, at the same time minimize the deflection, but they might oppose each other. It's not always possible that both of them are kind of directly proportional. So then what happens is we might end up with something like this plot. We call it as a Pareto plot. So where all these the lines that are, or the points that are in blue color, so they're all your optimal designs only. There's no one particular optimal design in this case. Why? Because it's multi-objective and you may not have a single result that time. So now the user, based on his experience and based on his requirement, he can pick any of these values as his optimal value. And we have techniques which support multi-objective optimization also. And then we'll talk about robust and reliable design. So sometimes what might happen, as you see, so maybe we start with the initial design and then we try to do an optimization. So it might fall somewhere close to the boundary. So in our case also, we saw that yeah, it is falling very close to the boundary. That's where we could get the minimum value of mass. So it is very close to the constraint boundary, as you see. So most of the times this is what would have happened. Then what will happen is, in case if there is any small change in your variables, so the variables could be any of the parameters that you are working, or any external parameters, like it could be an Young's module. So maybe you have used a particular value of Young's modules, but when it is actually going to production, maybe the dealer or the supplier is using some other uh, uh, a little change in Young's modules is there. So then what would have happened? It might fall on the other side of the constraint boundary, or if the sheet metal thickness that you have considered is around 5 mm, but ideally it's around 4.95, or maybe a little change is there, that delta change. So in case if that delta change is added into the model, so what would happen? Whether it will still be within that safe zone, or within feasible zone, or whether it will fall on the other side of the constraint boundary. So that you can understand when you try to run a reliable study, or Monte Carlo study. That where we add some level of variance into each of the parameters and see whether it's still falling within your feasible space or within the space that is required, or it is falling outside the space. So that way we can finally after this, so if you think, yeah, it's not fully reliable, maybe we will try to run a robust design study where we will end up with another design, but it is fully safe, as in, so if even with that small change in those Young's modulus or small change in the thickness, all the designs will still fall within your feasible design space. So that is the idea. So this way you're sure that whatever optimal design that you got is both robust and reliable. So rather than sometimes the only doing an optimization may not fully help you. It might if you add this small level of variance, some of the designs might fall on the other side of the boundary. So we are going one step ahead after optimization and trying to do a reliability and robustness study. Then we have approximations. So typical approximations are nothing but the meta models or the mathematical models that we create, so to kind of mimic the actual behavior of the simulation model. It creates a relation between your input and output. So in case if you are running a long running simulation, so maybe it's, you can imagine a crash simulation where it might take more than 24 hours or even more. So if you are taking that into optimization, then it might run forever. Like if you have to run some 100 iterations or something, so each one taking one day may not it may not be feasible computationally, and it might take a lot of time as well. So for that we try to create something called as the approximation models, which can create that mimic the behavior of the actual simulation model and create a relation between your input and output. So that way your overall runtime reduced drastically. Like, so if you have some 10 parameters, accordingly we might want some 30 or 40 iterations only, not like some 100 or 1,000 iterations that the optimization wants. So we can run those 20 or 30 design iterations DOE and create a relation between your input and output. So that way it can save a lot of time. At the same time, you're reducing your computational space as well. So overall original FE model, yeah, it might take a lot of time, but when you create that particular surrogate model or the meta model, yeah, your overall analysis time is within seconds only, because you're just solving a mathematical equation. So we can do the process of building the mathematical model in Eyesight, and definitely we would want to see if there is any error coming, like whatever the fit that we have created, whether it's good with the original value or not. So that you can also assess in Eyesight, and then yeah, go further to do any of your optimization or reliability studies. So yeah, surrogate model development from DOE and responses, so everything that you can work in Eyesight. And we have some methods like RSM, response surface method. So this is very commonly used. So we have, now we can support both linear, quadratic, and third degree and fourth degree as well. And with respect to some of the neural networks that are used nowadays, so RBF and EBF, so radial basis function, elliptical basis function. So we have these techniques also available, and similarly kriging autocorrelation methods. So we have enough techniques which can help you create that as well. So that is more on different techniques that Eyesight has in it, so to drive your whole process. So this is kind of just an overview on how components in Eyesight looks like. So this is typically the abacus component. So you can load a abacus component, and you can kind of see what the input results are, and sorry, the input parameters are, and accordingly you can run the abacus component and see what the output results are coming. So this is all it is. So in case if you have a CAE file, so if you want to change the geometry, then probably you need a CAE file. So even that you can kind of call inside the abacus component in Eyesight and kind of vary the parameters, and accordingly you can read the output ODP file as well. So typically if you load a input file, in Eyesight. So you'll be able to see all the information like the section information or the load or the material information. So all this you'll be able to see. Similarly, if the output file, the ODB file, if you load, you will be able to see all the outputs that you have requested. So be it the stress values or be it the reaction force, anything that we have requested. So all this will be available in the output information. And in case if you are going with the CA file, like I said, so it will show you the geometry information as well as required. And you can go and pick whatever parameters that you would want to change for your design exploration. Then this is on another component, that is data matching. So in case if you are doing some level of material calibration, or if you are looking for to fit your test results with your simulation results by changing some parameters within the model, so you can try to do it in Eyesight. So this is just a way of how you can configure this data matching component. And we first try to load the source information, that is the test result information, and both the X and Y source, and accordingly we try to create a plot, and from there we pick the simulation information as well, and both finally we will be able to plot both the plots, like the one is your target data and the other is your simulation data. So Eyesight has methods to kind of compare these two data. Now we have all these methods. So under data comparison tab, we can see the different methods. So you can pick any of them. So some of them were commonly used, like the sum of area difference in the y direction. So since it's changing in y, so we pick in the y direction. We can go pick this value, and it has some difference value currently. And using the optimization techniques, we can minimize this value. So that way, the parameter it changes the values of parameters and see how best it can fit this particular plot. So that's kind of more on the overview about Eyesight. So maybe I'll go through some case studies here. So this is a kind of a full vehicle level optimization that we have done. So Eyesight, it's not just with Abacus, so any other external tool if you have also, you should be able to integrate it within Eyesight. So I'll show you one example on that as well. So this is with Ford Motors that we did. So where this is a whole MDO process where the baseline crash and NVH and durability. So all the models were taken, and accordingly we have generated all the required designs, and from there we kind of collated both all this information and created a input output matrix and created a response surface method. From there we did the design optimization, and we were able to reduce around 5 pounds here. Similarly with this is with Jeep Cherokee model, a similar type of analysis has been done here. So start with the baseline analysis of Nasta analysis. So typically the crash and NVH models were taken, and from there design parameters were created, and we did the DOE matrix from there, and all the analysis was run, and finally we created a response surface model and went to the optimizations. And here we were able to reduce around 3% of weight. And these are some of the other examples from different OEMs. So this is from Ford, where we were able to kind of automate the whole process. Like you see, it's a very big process that we have created here. And overall something which was taking around 70 days to complete. So there are 55 designs, and it was taking around 70 days when they were doing it manually. And we were able to reduce it to around 4 days only with the fully automation. And this is on spring design optimization, where we were trying to reduce the mass of the spring by changing the dimensions of it. And this is on evaluating the spot weld uncertainty. So like I was telling, so in terms of reliability, if we want to understand how reliable your design is, so maybe if you add some level of variance in some of the parameters, some of the designs are falling on the other side. So that way you're able to understand how whether the design is reliable or not. And this is on this is from GM Powertrain actually. So it's a overall process automation of the model building or the finite element model. So we had from starting from the CAD, then trying to create a mesh, and even the modeling the mesh also. So all this was done within Eyesight, and finally we're able to create the whole assembly. As you see, so we started with the CAD, and we were able to create all the connections as well, and finally we were able to give the output. So this is all a complete automation. So not just the design exploration that you're seeing in the previous slide. So even if you want to create an automation for a different process that you're doing, you can link it and create it in Eyesight. So all the CAD models were taken and material data and others, and from there we were able to mesh the whole components and finally create bolts and verifying mass and correcting it if required. So all this was done in the automation process. So whatever was taking around 5 to 6 days for them to do manually, we were able to do it in 2 to 3 hours, the whole one single workflow. And these are some of the papers on, this is from Rolls-Royce on robust design. So they were trying to understand how robust the design is, trying to run the reliability study and trying to see if that particular design is robust or not. So, and this is another example on reliability based optimization. So where this is a hydraulic cylinder piston. So using Eyesight and Abacus, we have done this. The objective was to minimize the weight, overall weight. And as you see, the baseline was around 75% reliable. So these are the random variables or the variables that where we are adding some level of variance. The preload pressure, the friction coefficient. So they may not be exactly the same when it's going into production, right? So we've added some level of maybe 0.5% or 1% of variance we have added. And the initial optimal design that we got was only 50% reliable, as you see. So we are able to reduce around 11% of weight, but still the design is only 50%. So when we went ahead and did the robustness based reliability study, so we were able to get maybe not as good as previously, but around 8% of weight reduction we got, but the model is around 95% reliable. So this is what the customer wanted. They wanted a model which was 95% reliable. So we were able to achieve that. And yeah, so that is more on the slides that I have. So from here, maybe I'll quickly, I'll show you another, one more case study. So this is on iron ore blending optimization. I'm not sure if any of you are from the GOE background or any of you are from mining industry, but I'll quickly take you through this as well. So just to show you that Eyesight is not just for the regular simulation activities, but you can use it in multiple disciplines as well. So this is mostly on the iron ore processing and blending. So iron ore, it has innumerable possibilities of combinations that are required. So, and if you want to achieve the best earnings, which combination is good. So probably if you want to understand that, so you can do it in Eyesight as well. So this is just the flow chart of how it's done. So in case the cost price and equality of the blending product, so they heavily depend on the stockpile combination. So if we have X stockpiles and Y products, so there is a X into Y possible combinations. So different combinations are possible. So uh, trying to do this manually may not be feasible also. So Eyesight, since it can handle multiple parameters at a time, and it has enough optimization techniques within it, and also we have enough data analysis techniques, so it can suit it well to do this particular kind of an activity. So wherein we started with this Excel component has all the information. So we picked all the parameters that are required accordingly. Then we have a calculator component next to it, so which kind of calculates the overall cost. And finally, we've given some conditions also, like so in Eyesight you can give a particular condition. So as you see here, so this particular activity will work only if this condition is satisfied. So you can right click on this branch and you can always give a condition. So this was the condition that we have defined. So anything within this limits only, this should execute. So that kind of a condition you can define. And we were trying to calculate the overall cost and the overall FE average using the calculator component. And finally, we've used the pointer method to run the optimization, and accordingly, these were the parameter input or design variables that we are changing. And we had a constraint here, so the FE average should be within this limit or less than this limit. And the objective is to maximize your profit, your earnings. So this was the whole setup that we have done, and accordingly, this is just a different cases that we have considered as well. But overall, yeah, we were able to achieve the best optimal result. Probably after around close to 2,200 iterations somewhere, we were able to achieve the best result. Just to give you an idea, it's not just for the regular simulation domain. Probably if you're looking for any logistics or trying to minimize the overall cost, or any of your probably for any of a financial calculations, so you can use Eyesight for any of these applications as well. So with that, I will maybe quickly show you some of one quick example that I have. This is a snap latch. So probably this is something which is commonly used. So for any of your fittings, we try to use this. So for applications, yeah, it's versatile. So it's used for in almost all the applications. And this has some parameters, and also this part is fixed here, and we are applying some level of load here. So we just wanted to see how by changing a couple of parameters here, how is it affecting your output. So the objective is to modify these two parameters, the length and the height. So these two parameters we are playing with. At the same time, we would want to see what is the cost or what is the mass that is coming out when the deflection should be within this. Deflection should be exactly this 11 mm. So at this point, we would want to understand what the cost is coming out. So this is how the workflow could be. So there is Abacus here, and to kind of calculate the cost, we'll add a cost calculator next to it. I'll show you this example now. So when you open Eyesight, this is what you see. So we have the, as I said, these are the process components and these are the application components. So we have enough application components, of which probably most of the users of our users, they can generally use all this. But if in case if it's not here also, we can still automate the process. So I have my Abacus component. I'll just it's simple. You can just drag and drop it, and I'll try to load this particular file, the snap latch file. So I'll click so input information. I'll click browse, and probably here I will go into this folder. So I'll pick the CA file because I want to change the geometry. So when I click read the file, it will read all the information or all the parameter information that is available in the CAE file. As you see, it read all the information, and in this I'm interested in these two sketch parameters, the height and the length. So I pick these two parameters. So this is how you configure your input information. So accordingly, if you are trying to change your boundary conditions, or if you're trying to change any of your maybe the density information or the other material information, you can as well pick the parameters accordingly. And then we go to the output information, that is the ODB file. I'll try to load it. I have my ODB here, and then read. So it read all the output information here, and here I'm interested in this mass and also this the max U max. So these two information so my idea is to maintain particular displacement value of 11 mm. Accordingly, I want to see how the cost is coming. So this mass is okay, and Once this is done, I'll add a calculator next to this. So here I see both the parameters that I've picked previously in as outputs. So they become the input to this activity, as you see. So both my mass and the displacement information is here. Here I'll add a simple calculation. I'll call it as cost. So cost is nothing but it's equal to the mass times, I'll give a factor to it, 0.5. So say mass times maybe 0.15 or something. Yeah. So this is how I created a small relation between my mass and the cost. You can just click calculate to see if it's working fine. So yeah, cost value is coming something here, as you see. Click OK. So once this is done, I'll try to place a DOE on top just to give you an idea how to configure. So pick and over here I will, if I go to factors, I'm able to see both my input parameters, the height and the length. So I'll pick these two. Maybe I can go with any of these techniques here. For now, I'll quickly go with the full factorial. And maybe I'll go with some 4 levels. So overall, I'll get around 16 designs here. And in post processing, so I mean the values that I am interested in. So I'll go pick both the cost and the Umax. So these two are something I'm interested in. And my objective is to achieve this target. So target is around what? 0.011. So this is the 11 mm displacement is what my target is. Right? So I pick that and click apply. Click OK. Now I can run this, right? So it's as simple. So you can on fly create any of your workflow like this and just run it. If I go to logs, I should be able to see all the information, whether it's able to run the model properly or not. So it's able to run it. You see. So it might take some time. Maybe I'll kind of show you once it passes a couple of iterations. Yeah, it has done the first iteration accordingly. So you'll be able to get the information of your input parameters as well the output parameters here in the history tab. And if you go to SimFlow, here you can see the status of your run. So out of 16, yeah, 1 iteration is done. So others are still going on. Yeah, second iteration is also done. So accordingly, it goes on. Right? So in the interest of time, I'll quickly show you the final result, which I have it here. So this is the final result. So for all the 16 designs, and this is the best design. So it is close to the target. Rest all are kind of violating the target. So 0.011, right? So this is somewhat close to it. And this is the related cost value to it. So just to give you an idea how you can integrate an Abacus component and a calculator so as to do some level of design iteration. Then I have some more examples as well. I'll quickly show you that. So, okay, 1 second. So in case if you want to, if you have some other tool that you are working on and it's not available as a component in Eyesight, you can still try to create a workflow. So here, this is a quick kind of a ANSYS workflow that we have done. So in case if the user is using ANSYS and if he has multiple steps involved, so wherein first we are trying to change the CAD imagine, so we can directly use something called as a OS command here, so that can help you run the command line. So this is what we are doing. So first we are trying to modify the CAD, then we are doing the pre-processing here, overall pre-processing, and next we are solving the model as well. So if you have that particular command line which can run your tool, so you can bring into Eyesight and you can overall create the process. So finally we are doing post-processing as well. So all this was done within Eyesight, and so with using this particular command line, so we can integrate multiple steps also, be it a component that is within Eyesight or outside Eyesight, you can as well run it in Eyesight. And this is just another example wherein, in case if you are having a particular file where you have to change the input information and then run it. So you can use the data exchanger component or the sim code component that I have, where it has both the command line information and the input output information. So you can pick that ASCII file where you can change your parameter information, and accordingly can parse that information. Like you can pick this space and say, okay, this is my surface area, or you can say, okay, this is what the weight of the aircraft. So you can pick this and say and parse this information. So anything within this space is given to this value, so that every time a new set of information is given from the top, so that value is kind of modified here, and accordingly this file is saved. And when you run the file, the updated file gets into picture, and once you have a result as well. So the output information also, you can, again, if it's an ASCII file, you can read it into Eyesight and pick the values according. So here I'm picking actually a set of values. So all the distance information and velocity information. So this, it's writing out as a table. So I'm able to pick all this information here, as you see, for 42 lines of information is there, and all this you're able to write it out. So this you can take it as your response, or if it's only one value, like if you say the overall weight or some information that is coming out as an output, so that also you can parse it here. So this way, both you can modify your input information as well as you can read your output information. Both is possible. And the tool, you're running it through command line. So in outside Eyesight only. And in case if any of the this is another example mostly for the tire industry, if some of you are there. So if you have multiple processes that are connected from one activity to the other, so this is another example on that, where so first the axis half, and then you're creating the symmetric model, then creating the full model, and then if you have some simulations that you're doing based on that, so brake traction and free rolling, some of these activities are done one after the other. So all this is connected now. So the whatever information output that the first activity gives you, so you can call it in the second. Like if you go to the execution, you see that you're calling the old job also. So Eyesight can take care of maintaining the old job within that same folder. That way you can have the old job also when the new job is running, and it keeps on going for one activity to the other. This is another example on kind of automating the whole process. And I think that's sure. One second. Yeah, probably I guess that's all I have it from my side. Hope you got some insights about Eyesight. So this is a very simple tool, as you saw. I mean, you can very quickly configure it and try to run the model as well. So please start using it. So if you have any questions or any doubts, do reach out to us. We're always there.
Thank you, Bharat, for
Sure.
showing the material calibration or data matching as well. And I think
Okay.
there are no more questions. So we can definitely go ahead and wind up the session. And for the audience, if you have any questions, you can feel free to reach to us, and we can definitely help you out offline, be it with respect to the workflow that you intend to, or you want to know more about Eyesight, as well as how you can integrate it into your, work processes or day-to-day workflows. Please feel free to contact us. And once again, I thank all of you for your time and for attending this webinar as well. And also thank you, Bharat, for your time. and for a very insightful presentation as well as demonstration at the end of the session. And we hope the session was very helpful to all of you, and definitely we can connect offline. So thank you very much, and I hope you have a wonderful evening. Thank you very much.